We have already discussed about the simple harmonic motion using the case of a spring mass system, where we have shown that if a mass m is attached to a spring of spring constant k, it is able to oscillate back and forth, and the motion appears to be sinusoidal as a function of t. So the mass is displaced to and fro in between two maxima, a plus a and minus a, which is the amplitude of the motion, and these oscillations are sustained forever. This is a typical example of simple harmonic motion. Now, this is not the reality, because in practice we see that if we set such a system in oscillations, gradually the amplitude of oscillation goes on decreasing, and eventually the system comes to rest at the equilibrium position. So if we are supposed to represent this graphically, this appears to be like this. The system starts with some maximum amplitude, and as time passes, the amplitude of oscillation goes on decreasing. Now we must note that the time period of oscillation remains the same throughout, but the amplitude of oscillation goes on decreasing. So there must be a force coming into play other than the force responsible for this type of simple harmonic motion. If we remember, the force responsible for this is the restoring force produced or imposed by the spring, elastic nature of this spring. Now, in addition to this force, there is another force which is called as a damping force, which is always present in all the systems. The damping force is responsible for the dissipation of energy. That is, the energy given to the system at say t is equal to 0 is eventually dissipated, that is decreased. So the total energy is not the same throughout the motion, but it is dissipated to the surroundings. One such case of damping force can be friction. So if we oscillate a pendulum in air, we see that eventually the oscillations stop and the pendulum comes to rest at the equilibrium position. So even this type of motion is due to the damping forces existing in this system. So typical nature of a damping force for this case will be F being proportional to the speed. That is, larger is the speed, larger is the damping force. Further, this damping force is directed opposite to that of the speed. That is, if an object is moving in a positive x direction, so since the damping force opposes the motion, it has to be directed in a direction opposite to that of the v. So this is a typical nature of damping force. So just like this A, which is the constant of proportionality introduced here, we can also introduce another constant of proportionality, say B, in this case of damping force. So now we have to include two forces, namely the restoring force minus kx and the damping force minus bv when we write down the Newton's laws or the equations of motion. We note that v is by definition rate of change of displacement as a function of t. So if we apply Newton's law, it says that F bar is Fr bar plus Fd bar, that is m into A is minus kx minus b dx by dt. Now we must remember that this acceleration is the second order derivative of x with respect to t. So here we have m into d2x by dt squared plus, now this term taken on the left hand side becomes positive, so b times dx by dt, and this term taken on the left hand side also becomes positive, plus kx equal to 0. This can further be simplified if we divide throughout by m, so that gives us d2x by dt squared plus b by m dx by dt plus k by m x is equal to 0. Now as done earlier, let us define the constant k by m by some omega squared. Now there is another constant b by m. Let us denote it as 1 by tau. Why is it denoted as 1 by tau? That will be clear to us at the end of this discussion. So if we introduce these two constants in the equation above, we have to write d2x by dt squared plus 1 by tau dx by dt plus omega squared x is equal to 0. Now this is the equation of motion whose solution we have to find out. Now this is a typical second order linear homogeneous differential equation, and there are standard techniques to solve this equation. We can replace this d by dt by capital D, that is just a notation, which gives us d squared plus 1 by tau plus omega squared into x is equal to 0. So we are just replacing this d by dt by this capital D. So it gives us d squared x. Then we have 1 by tau into d is to be introduced here. So d into x into 1 by tau, that is dx 1 by tau, and the last term is omega square x as it is. Since x cannot be equal to 0 because x itself is the solution, the other bracket has to be 0. That is d squared plus 1 by tau d plus omega squared has to be equal to 0. This is called as auxiliary equation, and this can be solved by the standard technique of solving a quadratic equation. So clearly we can discuss of three cases. So since this is quadratic, it will have two possible roots. So there are three possible cases to be discussed. I will just brief about these three cases. When the roots are real and unequal, when the roots are equal, and the roots are complex conjugates. So the case which is of our interest is this one, because when we talk in terms of complex numbers, and the general solution to this is x equal to a e raised to alpha t plus b e raised to minus alpha t. This alpha is nothing but the roots which we are talking about. So if this alpha is imaginary or complex in general, we can use the Euler's formula which involves e raised to I theta being equal to cos theta plus I sin theta. So if this alpha is complex, then this entire solution is going to have cosine and sine term, which indicate an oscillatory behavior. In the other two cases, which will directly involve e raised to alpha t and e raised to minus alpha t, they will just provide an exponentially decreasing solution. So let us just focus on this last case and let us not go into the mathematics and try to derive the solution. If we solve this, the solution is of this particular form: x equal to a e raised to minus 1 by 2 tau times t into cos of omega dash t plus phi. This is a typical solution where omega dash is some new constant. Since it is complicated, we replace that complicated term by another constant omega dash. It is given as omega squared minus 1 by 2 tau bracket. Now if we compare this with the earlier equation of the simple harmonic motion, we can see the differences directly. In this case, the particle was oscillating with the frequency which was the natural frequency of the spring mass system, omega, characterized by k and m. But in this case, the frequency of oscillation is omega dash and not omega. So the frequency is slightly different. The other difference is that in this particular case of simple harmonic motion, the amplitude is fixed. So the amplitude is constant forever. So the oscillations are sustained for indefinite time. But in this case, as we can see, the amplitude part is a function of t. In fact, the amplitude decreases with respect to time exponentially. So what does that mean? If we try to plot the amplitude as a function of t, if it starts with some maximum value, say a, then as time passes, amplitude goes on decreasing. Amplitude goes on decreasing and it eventually reaches to 0. And with this exponential decreasing amplitude, the system is keeping on oscillating because there is a cosine function term existing. So this is the mathematically proved nature, which we have already discussed qualitatively somewhere here. Just recall this discussion. So yes, if we include the damping force, it causes the amplitude to decrease exponentially and the system can keep on oscillating just like the simple harmonic case, but with a decreasing amplitude. We can see what happens to the energy of the system. The formula for total energy is just half k a squared in case of simple harmonic motion. Now we have to replace this amplitude a by the modified amplitude a e raised to minus 1 by 2 tau into t. So total energy will be half k a squared e raised to minus t by tau. So yes, even the energy is going to be a decreasing function of time and eventually it will reach to a value equal to 0. So yes, the energy is dissipated by this damping force. So Why do we discuss this case? Because in reality, most of the system, or in fact all the systems, involve damping forces. So it is not possible to sustain the oscillations forever, and the oscillations die out eventually. Thank you.